Today is going to be a little different from the course seen so far. I mean, what we've covered so far has been computability theory stuff. And that's, I mean, if you were to like explain it very quickly and probably somewhat poorly, computability theory addresses the question, what can computers do, right? And so complexity theory, very closely related field, which is my research field as a PhD student here, does not ask what can computers do, but rather it asks what can computers do quickly? And more importantly for us, what can't they do quickly? And so right now, what you're looking at is the web or the homepage of the Clay Mathematics Institute. And specifically, it's their page on the Millennium Prize problems. So these are these 7 problems that they declared as being super duper mega ultra important in the year 2000. And to highlight just how super duper mega ultra important these problems were, they allocated a prize of $1 million to anyone who could solve any of the 7 problems. And so far, only one of them has been solved, and the dude didn't even want the prize money. So nobody's rolling in any Clay Mathematics Institute cash right now. But perhaps you could be, for one of the very problems on this list is one you may have heard of, the P versus NP problem, right there. Yeah. So who is this P? Who is this NP? And why do people care so much? These are going to be among some of the questions that we investigate in today's lecture. And they will today's lecture will also form the basis of a couple bonus questions that I'll throw on the assignment about this stuff. Yeah. All right. Any questions about what we're going to look at today? Yes. Oh, I think the one that got solved was the Poincaré conjecture. Oh yeah, right here. You can, I don't know much about this problem, but if you're interested, you should just, the website, you know, it's right here. So yeah, this is the only one that's been solved so far. Okay, any other questions? Any other questions? Yes. On the assignment, and the bonus question is not prove whether or not P is equal to NP, just to be clear. Yeah. Okay, so let's actually start looking at, you know, I think a natural starting place, if we're going to understand or try to understand why this problem is so important, is, well, what even are P and NP, right? And to do that, how do I change this? No, come back. Can I just, oh no, I'm still sharing on that thing. Okay. Ah, phenomenal. Okay, so yeah, what are P and NP? That's kind of going to be just the first thing that we look at today. And before we do that, well, I kind of said that complexity theory was about how long it takes computers to solve things, right? And you know, well, it's about a couple of different measures of complexity, but what we're going to be looking at specifically today is time complexity. A couple other resources of interest to complexity theorists are things like space complexity, randomness as well. But for the purposes of today's lecture, we're just going to be looking at time complexity, and that's really what the P versus NP question is, at least in its bare bones statement, is really all about. So, okay, how do we associate a notion of how long it takes computers to do something with this theoretical model of computation, the Turing machine that we've seen so far? Well, you kind of just do exactly what you'd expect, right? We defined the computation of a Turing machine as what? Just this sequence of configuration changes, right? So you can think of each configuration change as a step Yeah. And you can say that if M is some Turing machine, right? And T is some, time function, so to speak. You say that T is the running time of M, or that, M is a T n time Turing machine, if for all n and for all inputs over the alphabet of M, which I've just assumed to be 0, 1 for the sake of simplicity here, M halts on input X within Tn steps. So on every single input, right, of length n, M halts before it has reached its Tnth configuration change. Okay? Pretty standard, kind of exactly what you'd expect so far. Okay, so now that we have a notion of how long it, or the time of a computation is, what we can do is we can start defining complexity classes, which sort of bunch problems together according to how much of a certain resource they need. And the first such complexity class that we'll look at is the deterministic time complexity class of T, which is in definition 2 over here. And we're going to denote it as this thing d time of T. And it's just the set of all problems that are decidable by a big O of Tn time Turing machine. Okay? So before the only complexity classes we've sort of seen so far have been these really big things about computability, right? There was like the Turing recognizable problems, and then there was the decidable problems contained in that. And now within the decidable problems, we're looking at even smaller classes that we're defining using this notion of time so far, right? So you can define a class like this for every function T that you want, basically. And so then this P that you heard in the P versus NP problem is just this polynomial time complexity class defined as the union of all of these time complexity classes where the time bound is some polynomial, right? Over all polynomials. Okay? Any questions about this so far? Pretty expected definitions, kind of. Yeah. Okay, then. So now, so far I've just spit a bunch of words at you, right? There's no real intuition attached to anything I've said. Like, oh, well, why have we defined P? Why have we given like $1 million hit on a problem that depends on P, right? With this like polynomial definition of time classes. Why polynomials specifically? Well, it's because intuitively, complexity theorists and the theory community at large, really, there's this association of P with efficiently solvable problems. Intuitively, we understand a problem to be in P if there's some efficient algorithm that solves it on some reasonable model of computation. Okay? And okay, so why polynomial, right? Why not, I don't know, exponential or doubly exponential or anything else, right? Well, there's two kind of reasons for this. The first is that when we looked at the Church-Turing thesis, we showed that the Turing machine was, in some sense, equivalent to all reasonable models of computation, right? And it turns out the Turing machine is, in fact, polynomially equivalent to all these reasonable models, meaning it can simulate any one of them with a polynomial overhead kind of in the runtime of whatever that other reasonable model of computation is. So all these reasonable models of computation linked loosely together by the Church-Turing thesis, well, they all apparently, they seem capable of simulating each other, and the overhead that you get is polynomial for all of them. Like, for instance, one result is that multi-tape Turing machines can be simulated by single-tape Turing machines with a quadratic overhead. So if it takes, t squared n steps for a multi-tape Turing machine to do something, or sorry, if it takes Tn steps for a multi-tape Turing machine to do something, you can expect a single-tape Turing machine to be able to do the exact same thing with t squared n steps. And that's a result in 7.1 of the textbook. It's nothing crazy. We're not going to look at it here because it's more of a high level day. So this is the first reason why we chose polynomials to associate with reasonable computation. And the other reason is that when you look at any sort of problem that you care about in the real world, there's always a really, like a lot of the time, there's a really dumb way of doing it, right? And it goes something like, just try every possible thing that could work and see if it works. The so-called brute force approach, right? And with respect to the size of the input of your problem, the brute force approach is generally exponential time, right? It's just something we've seen from previous algorithms courses. Really, the whole cell of algorithms as a field and as a course that you've studied is that there are more intelligent ways of doing an exponential brute force search over some problem, right? And what more intelligent means is exploiting some structure of the actual problem using an algorithm that gets you down to polynomial time, which is little o of any exponential runtime that you might see, right? So in some sense, polynomial also means you did something smart. Yeah, and this is the other reason why we associate P with this interesting class of reasonable problems that we can efficiently solve. Okay, so, and yes, you can sort of define similarly to the way we've defined P, this exponential time complexity class, exp, and that's just the union of all these d times where the union now is over the exponent of the n and the exponent, right? It's just exponential time. And it's not hard to see that, well, I guess we'll point this out a little later, but P is in exp, right? Because if you could do something in polynomial time, you can do it in exponential time, just trivially. So, okay, let's see a couple examples. Well, before I continue, are there any questions about the definitions we've seen so far? Or anything as to their motivation, perhaps? No? All right, cool. So let's look at a couple examples of problems that are in P. So a lot of really important, relevant to many concrete areas of computer science problems turn out to be in P. This first example here, man, can you get this to like, there we go, perfect, that was annoying. So a really simple problem it's not hard to see is in P is this problem path, where you just give me an encoding of a graph, and I just want to know, is there a path from some node S in the graph to some node T? And, you know, the way that you would solve this with an algorithm is you just like search through the graph, and it's, you know, polynomial time, right? Not hard to see that path is in P. But you also have some more interesting problems in P, like the problem of determining whether a matrix is invertible, right? How do you do that? You just do Gaussian elimination as an O(n) cubed runtime, yeah? Another example of a problem in P is this sort of decision problem version of max flow, where you want to know if flow network G with integral edge capacities C achieves some flow K, right? And, you know, this is like, then you have this decision problem opt, which is just encodings of sort of linear constraint optimization problems, right? And the reason why we know, right? So we have this standard form version of an optimization problem, a linear optimization problem, and we want to know if the optimal value achieves value at least K under the objective function C. And the reason why we know this is in P is because of Ford-Fulkerson, and the reason why we know this is in P is because of the simplex algorithm, right? Or not, I don't think the simplex algorithm actually, but there are polynomial time algorithms that solve the optimization problem. And it turns out that there's some really surprising problems in P, like the problem of just determining whether or not binary encoding is prime, encodes a prime number. We didn't know this until 2002, actually. There's this big result, the AKS primality test. And we've actually, in some of the problems, or the Turing machines that we've given to show that computability theory problems are decidable, were actually, they ran in polynomial time, right? Such as ACFG and ECFG. Yeah. So, all right, there's a bunch of problems people care about in P. Yeah. And for each of these, you can see that there's something smarter than the dumbest thing, the exponential time algorithm, happening, right? Because the dumbest thing for, say, path would be to try every possible path, right? That would take exponential time. The dumbest thing for, I don't know, the optimization problem would just be to try every single vertex in your feasible region. Another thing that we're doing something a little more intelligent than, right? So you can see why, a definition aside, just intuitively, P is contained in X, right? Okay, so now we've seen who this P guy is, but there was another person in this P versus NP question. It was this other class, NP, right? And we can define, it turns out that NP is defined pretty much the exact same way that P is defined, just with non-deterministic Turing machines instead of deterministic Turing machines. So the non-deterministic time complexity class of T, which we denote as N time of T, is the set of all problems decidable by a big O of Tn time non-deterministic Turing machine. Okay? And so P, or NP, is then the non-deterministic polynomial time complexity class NP, is defined analogously in the way that you would expect NP, except it's just all decision problems that are decided by some non-deterministic Turing machine running in polynomial time for n to the k for some k, constant k. Okay? Now, you may be wondering to yourself, well, so I've told you that this question of whether or not P is equal to NP has many practical bearings on, you know, things that people across computer science do in the real world that they care about. So it may seem a bit curious at first that I have defined NP this way, right? Because non-determinism doesn't seem to be at all a reasonable model of computation, right? I mean, how did non-determinism work? We had some like esoteric wizard knowledge in our algorithm that was sort of guessing the correct thing to do every single time, right? And there were these branches of computation that don't, you know, that's not how real computers work. Yeah. They have a single branch, a deterministic branch of steps, one following from the next. And they don't have access to this magic of non-determinism. So why then is there $1 million hit on NP, right? A question involving NP. And the answer to this becomes much clearer when you look at an equivalent way of defining NP, or a different but equivalent way of defining NP. So we're going to define as a preliminary for this definition, I'm going to define a special type of multi-tape Turing machine called a verifier. Okay? And it's a two-tape deterministic Turing machine that we'll call V, with its second tape is going to be this special read-only tape that we'll call the certificate tape. Okay? Now, given two strings, x and y, we'll denote by V on input x with certificate y, this computation of V with x on its input tape, and starting configuration consisting of x on the input tape, and on the certificate tape, y is printed. Okay? So a starting configuration of a verifier is a bit different. There's a little more to it than the starting configuration of an ordinary Turing machine, right? It's given these two strings, whereas before it was only given the input. Now it's given the input and this thing called a certificate. Okay? And if V accepts X with certificate Y, then we say that Y is a certificate or witness of X. Now, why have I defined this thing? The alternative definition of NP is as follows. NP is the class of all problems L for which there exists a polynomial time verifier such that for all X, right, over the set of all strings, where sigma here is the alphabet of L, X is in the language L if and only if there is some certificate witnessing X's membership in the language L. So maybe it doesn't seem clear why these definitions are equivalent at first, or how. I mean, we've sucked all the non-determinism out of this definition or characterization of NP with the verifier, right? Because V is a deterministic Turing machine. It has this extra input, but everything it does, given those two inputs, is deterministic. So then the question becomes, how is this equivalent to the definition I saw that I gave of NP just a few moments ago? And to answer that question, I think it'll be useful to see an example of a problem in NP. So we're going to define a problem called Hamiltonian path, denoted Han path here, okay? And this problem, its instances look like this. G is a graph, S is some starting vertex in G, T is some ending vertex in G, and I want to know, is G a graph with an ST Hamiltonian path now? Where a path from S to T is said to be Hamiltonian if that path P visits every vertex in V exactly once. So it doesn't visit the same thing again. And if you've already taken 360, you are probably quite familiar with this problem. Any questions about the statement of Hamiltonian path or what a Hamiltonian path is? See an example. So here's some graph. It's the planar kind of encoding of the dodecahedron. Is there a Hamiltonian, and here's my S vertex over here, and here's my T vertex. So is there an ST Hamiltonian path in this guy? What do we think? Does anyone kind of see, how to get from that to that guy while visiting each vertex exactly once somehow? What do we think? Yeah, okay, I see something. There's hand in back. You think so? Okay, yeah. I'll work with that. There were also some head nods. You guys are right. Here's what a Hamiltonian path would look like from S to T. Starts over here with S. You just follow these arrows going along, visiting each vertex exactly once until you end up at T, right? And this, I like Hamiltonian path a lot because it really helps illustrate kind of the equivalence of these two definitions of NP. Because when you alone, right, without anything else, you were just given input, this GST here, were asked to find a Hamiltonian path, right, in this graph. I mean, you were able to do it, but it takes a little while, right? You got to try a bunch of things and then, see, maybe that works, maybe that doesn't work. But when you were given the actual, or a candidate, so to speak, for a Hamiltonian path, it was really easy to verify then that this graph is in fact in Ham path, right? And so here, the input to the first tape kind of my verifier was just the Hamiltonian, like this graph and S and T, right? But what the verifier gets is, this is what a regular Turing machine would get, okay? What a verifier would get is it would get the encoding, right, just of the graph itself, and it would get a possible Hamiltonian path, some sequence of vertices that could be a Hamiltonian path. And what it has to do then is verify using the certificate, this sequence of vertices, whether or not it actually is, in fact, a Hamiltonian path in this graph is in ham path. Okay? Now, why should this be equivalent to the non-deterministic definition of NP that I gave earlier? Because, okay, now let's suppose you're given this graph as input, but you're no longer an ordinary deterministic Turing machine, but you're now a non-deterministic Turing machine. What that means is you can make non-deterministic guesses. What are your non-deterministic guesses going to be to help you determine whether or not this thing is in ham path? There was one problem on part 1 of the 4th assignment that did something similar, right? The non-deterministic choices were, what is the next vertex in my path that could be Hamiltonian, right? So in some sense, the certificate is just the sequence of non-deterministic choices that causes your non-deterministic Turing machine to accept. And your verifier is given this sequence, right? Because you know that if a non-deterministic Turing machine that recognizes or decides ham path outputs 1 on this, right? It's because it was able to non-deterministically guess the certificate that if given to the verifier, it would accept on, given this instance. Does that make sense to everyone? Are there any questions about what I just said? So in particular, we see that ham path is then in NP. And we'll prove that using this verifier characterization. We'll give a verifier, a polynomial time verifier for ham path, assuming this would actually work with me. Oh no, why isn't this? Okay, cool. So here is a verifier for ham path. So it receives an input, right? Some encoding of the graph and S and T, and additionally, this certificate P. And what our verifier is going to expect the certificate to be is this sequence of vertices that is a Hamiltonian path, right? And so it checks or verifies precisely that. First, it checks, well, is V1 the first thing in this path S? Because if it's not, you can immediately reject. Give me another certificate. Give me something else, right? Because the same way that we only needed one accepting branch of computation for a non-deterministic Turing machine to accept, we only need one certificate on which the Turing machine accepts on this input for it to declare that that input is in the language ham path, right? So, okay, then it just checks that this thing is in fact a path. It makes sure that each VI is adjacent to the VI minus 1. If not, it rejects. And it makes sure it hasn't already been marked. Because as we walk along this path, we're going to mark the vertices that we see so that at the end, we know whether or not we've marked everything. Because a Hamiltonian path needs to visit every vertex exactly once. Yeah? And after it's done this, it checks, is the last thing T? If not, reject. And otherwise, well, we know that we visited every vertex in this path exactly once. So if that path visited everything, then we can accept we found a Hamiltonian path. Okay? Does this verifier make sense? Yeah? Any questions? Cool. So, yeah, I kind of jumped the gun on this question 16, but a nice thing to think about is what I kind of got at earlier already, which was, well, if you wanted to show that this thing was in NP by just giving a non-deterministic polynomial time Turing machine instead of a verifier, the way you would go about doing that is by essentially guessing, right, non-deterministically, what this correct certificate would be. Yeah? Okay, so This makes NP, like this alternative characterization of NP, makes it seem much more applicable to the real world. Because in the verifier, there's no non-determinism, right? In the verifier definition, it sort of characterizes NP as the class of problems that are efficiently verifiable, right? Given a certificate, okay? So where P is the class of problems that are efficiently solvable, decision problems that are efficiently solvable, NP then is the class of problems that are efficiently verifiable. And what the P equals NP question asks is this in fact the same class of problems? Can you efficiently solve everything that you can efficiently verify? Do certificates not give computers any added edge? Yeah? In terms of runtime. So let's take a look at some other problems in NP to try and sell you more on why this is a class of interest. So there are a ton of really natural, really important problems that fall in NP. First, you can kind of define a variant of Hamiltonian path where the graph is just directed. And it turns out that is also an NP. Using a very similar, you could give a very similar verifier to what we just gave. But there's also a ton of other problems, like for instance, this language cover, which accepts as input a graph G and a number K, and accepts if G is a graph with a vertex cover of size K. So why is this an NP? What if you're a verifier for cover and I give you a graph and you want to know, does it contain a vertex cover of size at most K? What would your certificate be that would prove to you that that's the case? Because a vertex cover, right? We say a set of vertices is a vertex cover if every other vertex in the graph is adjacent to some vertex in that set cover, right? So what would I have to give you as a verifier to convince you? Yeah, exactly that. It would just be the actual candidate for the vertex cover itself. And then it turns out it's hard, right, to actually find a vertex cover, but verifying it is super easy and can be done in polynomial time. You just check, doing a similar marking procedure, is every single vertex touched by some vertex in my set, and are there at most K vertices in the set, right? The traveling salesman problem, TSP, is another example of a problem in NP. So G is a directed graph, right? We accept this instance where G is a graph, D is some distance function on the edges of the graph, and K is a number. If there is a Hamiltonian cycle now, defined similarly to a Hamiltonian path, except S and T are the same vertex, of distance at most K, right? So there's some way of walking around the entire graph such that every vertex is visited exactly once. You start where you end where you started, and the total distance you've walked is less than K, right? And this is like a problem that appears in, you know, you could encode, G could be like some encoding of cities on a map, airplanes, right, for routing a problem. This encodes a lot of very, you know, present problems in the world that we live in. Another example of a problem in NP is 3 coloring. So here, it's just the instances are graphs, and I want to know, does graph G contain a 3 coloring? If you're a verifier for 3 coloring, what kind of certificate are you looking for? Yeah, exactly, just the coloring, because it's really easy to check if a coloring is a 3 coloring, right? And there are all these other problems like this is sort of like this as well. There's the subset sum problem, which encodes some set of numbers S and some other number K. And you want to know if there is some multiset in S such that the sum of its elements is exactly K, right? Another problem in NP, quite famous, is SAT, the Boolean satisfiability problem. Here, the inputs are Boolean formulas, right? ands and ors of Boolean literals over variables, okay? And you want to know if that formula is satisfiable. In other words, if there is some assignment that when you assign those values to the variable in your formula, the formula ends up evaluating to true, right? This is also an NP, and the certificate is precisely the assignment that sets it to true. And then there's this variant of SAT called 3-SAT, where it's the same thing as SAT, except the formulas are a little more structured. There are now these things called 3-CNFs, where CNF just means conjunctive normal form. In other words, phi here is an and of ors, each containing 3 variables. That's what a 3-CNF is. And all these problems are an NP. Now, an interesting, I guess not really interesting, but kind of obvious thing to note is that sort of the way that we saw it for P, the example problems that we gave, for all of them, there was a really dumb thing you could do, right, that ran in exponential time. For any problem in NP, that's also the case. Why? Give me a deterministic algorithm that solves any problem that has a polynomial time NP verifier. How do you do it? Yeah. Exactly, right? It's exactly the dumb thing. You just try every possible certificate. And because your polynomial time verifier is polynomial time, then there will be exponentially many certificates to try, right? Because a certificate can only have length at most polynomial, because your Turing machine can only watch or look at most polynomially many bits in the certificate. Okay. Now, that's one kind of trivial fact about NP. The other is that P is contained in NP. Why is this? Can you give me a, yeah. Exactly, right? If you solve the problem, you sure as hell have the certificate. It's the solution, right? In other words, you could come up with a dumb verifier that doesn't use any certificate. It just solves the problem, right? In polynomial time. So P is also an NP. And so extra credit question, is P equal to NP? If you're able to solve this, you should tell me and no one else, and I will give you some extra credit for your solution. Yeah, so this is kind of the, now we have like, hopefully you guys have a much more intuitive sense of like what P is, what NP is, and why they matter, and why the problem is non-trivial. Because it turns out for all these problems that I've given you up here in NP, the best deterministic algorithm, not done by a verifier, no non-determinism, just a plain old deterministic algorithm, time-wise, that can solve each of these is basically exponential. We don't know how to do anything better in the worst case than brute force for each of these problems. Yeah? So in some sense, the question asks, is a large class of really important problems efficiently solvable? Or are we doomed to always just doing the dumbest thing, you know? So, all right, let's transport ourselves back in time and imagine it's the late 1960s, early 1970s, and you're a young complexity theory researcher, okay? Maybe you don't have too many brain cells left after Woodstock to ponder this question, but you start asking yourself, well, if I have to prove that P is equal to NP, do I really have to give a polynomial time algorithm for every problem in NP? I mean, that sounds exhausting, right? There are hundreds of natural problems in NP that are out there that have been sort of cataloged. And even if you were to come up with a polynomial time algorithm for every single one of those problems, how do you know when you're done? How do you know when you've found all the problems in NP and given a polynomial time algorithm for them? Well, it would be useful if there was some tool that we had that perhaps we've already seen in the course that related the solvability of problems with each other. Huh. Is there some kind of formalization perhaps where if I knew I had an algorithm that solved one problem, I obtained an algorithm that solved another? Yeah, bingo, reductions. Reductions. Maybe we don't need to give a polynomial time algorithm for every single problem in NP. Maybe there's some way of relating some problems in NP together, such that there's only like a handful of problems, ideally, that I need to give polynomial time algorithms for, that through this network of reductions will knock out the rest of the problems in NP. All right? But there's a subtlety here, which is the way that we defined reductions, like mapping reductions, for instance, so far, it's not really going to cut it for the purposes of giving efficient algorithms, assuming the existence of other ones, right? Because in some sense, the Turing machine that computed the mapping reduction, all we said was that it had to be a decider, right? But that's not what we want here. We want something more. We want to say that if we have a polynomial time algorithm that solves some problem B, then we want to get an efficient algorithm for A that uses our algorithm for B. We also want the reduction itself to be efficient, right? Because otherwise, I mean, there's no point. Your reduction could just be exponential time, do the dumb thing, and not even look at the algorithm that you assume exists for B. Yeah? So we're going to need to refine our notion of a reduction a little bit if this is going to work. Okay? And so, oh, well, there's 220s here, but if you're given some function f, oh no, we'll say that, because when we defined mapping reductions, we defined what a computable function is. So to refine our notion of a reduction, we'll develop an analogous notion of a time-bounded computable function. We'll say that a function is t-time computable if there is a t-time Turing machine f that computes f, or capital F that computes little f, right? So on every input, it halts with, on its tape, the output of the function that computes, and it does so within time t, the length of that input, right? Pretty much what you'd expect. Okay, so with this in hand, we can now define the notion of a polynomial time mapping reduction. So if A and B are two decision problems, we'll say that A is polynomial time mapping reducible to B, and we'll denote that with A less than or equal to P here, right? Whereas before it was an M, here we're just using a P to indicate this, or polynomial. And we'll say that this is the case if there is some K such that there is an n to the K time computable mapping reduction from A to B. So this F runs in polynomial time for some polynomial, okay? Are we all clear on this? Any questions so far? Great. All right. So, and this is the right notion that we want, yeah? Because it's really not hard to prove that if A is polytime mapping reducible to B, right? If we suppose that, then if it turns out that B is polytime solvable, right? Then A is polytime solvable. You just put your mapping reduction and the algorithm for B together, and you get an algorithm for A. Voila. We had a very similar corollary kind of the definition that we gave for mapping reductions with decidability instead of membership in P. Yeah, and here it's kind of the exact same thing. But what we want for our purposes of attacking the P equals NP question. Okay? So let's see an example of a polytime mapping reduction. And I think that when I was taking this course for the first time, and we got like way back in my undergrad, and we started looking at polytime reductions between problems in NP, that was really where I started to gravitate personally towards complexity theory as a field of research, because I think that polytime mapping reductions between problems in NP is some of the coolest things that you can see in an undergrad course. And we'll see why in a second. We'll give an example of one. So let's show that 3-SAT is polytime mapping reducible to directed Hamiltonian path. Okay. Now, I'm only going to give a sketch of this proof, but it'll be all the important details, and you can flesh it out on your own, given this. So, okay, let's take a closer look at what exactly 3-SAT is, because I kind of glossed over it in a sec earlier. So the input to my mapping, this Turing machine that's going to compute my mapping reduction F is going to be a 3CNF formula over some list of Boolean variables x1 through xl. What does that mean? It means that phi, my 3CNF formula, looks like this. It's an and of a bunch of clauses, right, which are just ors of literals. Let's say m of them. And each clause CJ looks like this. It's the or of 3 literals, where each of these literals are just over my list of variables. Okay, so this is either, like possibly x3 naught, x5, and x6 naught. An example of some literals. And this is what a 3CNF formula looks like. Okay, and of clauses of width 3. Yeah, so the input to the reduction is going to be this. And I want to do something that may seem like a bit crazy or impossible at first, which is I want to take an instance of a 3-SAT problem, a Boolean formula, and somehow transform it into a seemingly totally different mathematical object. I want to turn it into a directed graph, G, with some designated vertices S and T, such that there is a satisfying assignment of my input formula, if and only if there is a Hamiltonian ST path in this graph G that I construct. These, a priori, these mathematical objects look very, very different from each other, graphs and Boolean formulas, yeah? And yet somehow we're going to give a reduction that relates the two problems together by investigating the innate computational hardness of each one. So let's see how we're going to do this. Take a drink of water and pause for a sec if anyone has any questions. Well, so what would you need to do to show that P is equal to NP right now so far? Well, before we started talking about reductions, what you'd need to do is you would need to show that every single problem in NP, so every single problem in that list that I gave earlier, and a bunch of others that I haven't shown because I can't, it'd just be too many, all have polynomial time algorithms, right? And we don't know that that's the case. In fact, we don't even know currently how to show that there is a polynomial time algorithm for a single problem in NP. Brute force is the best that we know how to do when you're just looking at deterministic run-of-the-mill Turing machines. Oh, well, here's the thing, right? Just because you can't find a polynomial time algorithm for a problem in NP doesn't necessarily mean one doesn't exist. And so you could resolve the P versus NP question in one of two ways. You could either show definitively P is equal to NP by giving a polynomial time algorithm for every problem in NP, or you could show that it's not, that P is not equal to NP by showing that there is some problem in NP that has no polynomial time algorithm. But you have to prove that. It's not enough to just say, I tried a bunch. It seems too hard. It's probably the case. And the proof, the actual proving of P being not equal to NP That's the whole reason why I have a job, basically. Any other question? That was a good question. Any other questions about what we've seen so far? Yeah. Other way around with this reduction that we're giving, right? Yeah. So this is why like people were first interested in polynomial time mapping reductions. It's because of exactly what you're saying. Now, instead of coming up with one polynomial time algorithm to solve this and one polynomial time algorithm to solve this, I can just come up with a polynomial time algorithm to solve this and then give a mapping, because I know this mapping reduction is here or exists. I will have also obtained a polynomial time algorithm to solve 3-sat. And well, you may have your thought process may be, well, you're still proving two things, but it seems a lot easier to show that you can solve a hard problem with another hard problem than to show that you can solve both hard problems. Does that make sense? Because you can leverage the fact that this is a hard problem and that it seems to require a more powerful model of computation for it to be way easier to decide 3-sat than if you were just working with nothing. Does that make sense? Any other questions? Good questions. All right. So let's take a look at an example reduction, or a sketch kind of a reduction. So our input is going to be this 3CNF formula. And what I want to output is a graph G with two nodes S and T, such that this if and only if holds, right? And moreover, because it's a polynomial time mapping reduction, I want this construction to run in polynomial time, right? That's the real crux here. So let's see how we're going to do this. So I'm going to show you a picture that looks a little wonky, but just bear with me and don't flinch for a second. Behold, an encoding of a 3CNF problem as a graph, a directed graph. And I claim to you that there is a satisfying assignment to the original formula if and only if there's a Hamiltonian path through this monster. Okay? What is actually going on here? What is this thing? Well, in any reduction from one problem to a problem of a very different type, what you end up doing is coming up with these things called gadgets. And what a gadget is it just encodes a certain part of your original problem as some analogous or isomorphic structure in the problem that we're reducing to. So our 3CNF formula is made up of variables, right? X1 through XL, and clauses. There's M of them, each consisting of an OR of 3 variables. Yeah? So what we'll do is we want to have a gadget for each variable and a gadget for each clause. Okay, what does that mean? Well, each one of these, I claim to you that each one of these diamond structures here is the gadget, intuitively, this kind of the encoding of my variables. For my variable x1, I have this part of my graph here, encoding x1. For x2, I have another one of these weird diamond structures. And I have another one for every single xi, up all the way up to xl. I have another one for xl. Okay. And then my clause gadgets, in other words, the structures that are going to encode my clauses, are going to be these sort of nodes over here on the side. I'm going to have one node for each clause in my input Boolean formula. And what remains then is, how do we wire these things up in such a way that if there's a Hamiltonian path through this graph, I can recover a satisfying assignment to my input Boolean formula. And the way that it works is like this. So let's take a close-up. Let's say, let's let xi be an arbitrary variable, and let's let cj be some arbitrary clause. So here's a close-up of one of these diamond gadgets, the diamond gadget for xi. So the way that we'll wire up our ith variable gadget with our jth clause gadget is we have this sort of row in the middle of a bunch of variables where each one is connected bidirectionally to each adjacent one. And we're going to have a pair, sort of an adjacent pair of each of these two middle variables in this row here, one for each clause gadget. And the way that I'll wire up my clause gadget to my variable gadget is I will connect the corresponding nodes in the variable gadget to my clause gadget with the direction of my edges depending on the literal contained in that clause. Because as you may have noticed here, there was one pair of these things for my C1 gadget, which I encoded in blue, then some separator. All the separators are in red. There was one pair of these row nodes for C2, right? And there's going to be like some arrows connecting those guys. And for every single clause gadget, there will be an adjacent pair corresponding to the color of the clause gadget, like this, contained in this middle row of variables. And this is the case for every single one of my diamond gadgets, because then I'm also going to wire up C1 in the second guy the same way. C2 in the second guy, also the same way. And I do this, I have such a pair for every single clause gadget all the way up to CM, right, which I've denoted in purple here. And between each pair of these variables, I've added a red separator node. And I'll explain the purpose of that in a moment. But how, the question then, where we're going with this is that an assignment to the variables will correspond to a path, a zigzagging path through each of these gadgets, where if I assign x1 to be true, then the corresponding path through my x1 gadget is going to be this one. And if I assign it to be false, the corresponding path through my x1 gadget is going to be this one. And then maybe I assign x1, so I assign x1 to false, then perhaps I assign x2 to true. And so you can see that each variable assignment induces a portion of the path as it goes through the corresponding gadget. But where do these clause gadgets come in? Well, what does it mean for a truth assignment to satisfy a 3CNF? It means that in every single 3CNF, which is an OR of three literals, one of them is true, right? And I need this for every single one of my clauses. So intuitively, I'm going to wire these clause gadgets up to each variable gadget such that if the assignment of x1 to true makes clause 1 true, then this path will take a detour, cover that guy, go back to the other one, and continue going through. So then all of the clauses being assigned to true corresponds to my path hitting all of the clause gadgets and therefore being Hamiltonian in the graph that I'm constructing. Is that starting to make sense? Yeah? So let's take a closer look at how we're going to wire up each of these clause gadgets to our variable gadgets. So look back at this example. We'll cover three cases. The case where xi is a literal in CJ, where the negated literal xi appears in clause CJ. That'll be our second case. And the third case is that this variable neither of its literals just appears in that clause. So in the first case, if I could just get this thing to collaborate with me. So in the case where the positive literal xi is contained in the jth clause, we'll wire it up, because remember, an assignment of 1 to true corresponded to a path that went like this, right? So I want to make sure that if a positive literal is here, and I'm assigning this to true, this guy gets satisfied, and therefore this guy can be covered by my Hamiltonian path. So I'm going to wire this gadget up such that the arrow to CJ, or the edge to CJ, is the left one, and the arrow or edge from CJ is the right one, right? Because this will enable that path to hit CJ as it moves along, right? And we'll wire it up, we'll switch it and wire them up in the opposite way if the negated variable xi appears in CJ, right? Because then what's going to happen is I'm assigning this to an assignment to 0 over here now should satisfy this clause. Therefore, I want to make it so that when this path goes through the graph, it has the opportunity to cover this clause and go along, right? And we do this for each CJ and each CI. Oh, and the last case, which is when this variable doesn't appear among the 3 literals of CJ, is that we just won't connect it. Okay? So you can see that, if xi now, say, it's the case that the positive literal appears in CJ, but we assign x1 to be false, then because it's a directed Hamiltonian path, I can't go over here in order to hit this guy. I need to rely on some future xi to take care of that for me, assuming it's satisfiable. Some xi where the literal is negative, yeah? And so you do this wiring between your clause gadgets and your variable gadgets for every single one of them, and that's how you get this graph. Oh, and then you call S this little vertex that sits at the top of this whole thing, and T this vertex that sits at the bottom of the whole thing. And then hopefully it's not too hard to see that there is a satisfying assignment to my original Boolean formula if and only if there is an ST path that hits every single variable somehow, right? For every single node and ends at T. Yeah, that's intuitively how this construction works at a high level. So we've like transformed the hardness of one problem into the hardness or difficulty of a seemingly totally unrelated problem. And they're linked together. The only sort of shared thread between them is the innate computational difficulty of a problem sort of being an NP, right? We've taken the same hardness and manifested it, it seems, in 2 different computational problems. Kind of magical. Yeah. And and the final thing that you have to show is that this entire construction runs in polynomial time. But that's not too hard to show because you're going to have L of these variable gadgets, M of these clause gadgets, each of which is linear in your input size. And you have 3 times M for the number of clauses of these sort of row nodes over here, right? 3 times because there's a pair for each clause plus a separator variable, plus 1 technically, because there's this last guy. And the reason why the separator variable or the separator nodes are present, which you may have been wondering, is because I need the if and the only if for my reduction to work. And one pathological case, perhaps, that could occur in this construction is if, I shoot off to satisfy this CJ, but then maybe I skip a bunch of these intermediate variable gadgets and go all the way down here, and then, work my way back up somehow, perhaps. But Uh, Essentially, these variable gadgets make it so that that's impossible. They force any departing path that goes to satisfy or hit some clause to return, because the only chance that this path will have to hit that separator variable is if it comes back here first. It can't go anywhere else. Does that make sense? So it forces your Hamiltonian, these separator nodes force your Hamiltonian path to behave nicely in the way that you want for your reduction. And if you want to see the full kind of proof of this, is a really good coverage in the textbook SIPSR in section 7.5, I think. Okay, so wow, we've seen what a polynomial time mapping reduction between two problems in NP looks like. And well, the idea was that, you know, perhaps now we've simplified the task a bit of proving that P is equal to NP. Maybe I don't need to come up with a polynomial time algorithm that solves every problem. Maybe I can exploit these sort of reductions between problems to simplify the task. I have two options now, right? Suppose I want to prove that P is equal to NP, then I have to prove that there's a polynomial time algorithm for every problem in NP. But for any problem in NP, I now have two options to do that. I can either give a polynomial time algorithm directly deciding A, or I could just show it reduces to some problem B for which I've already done that. Yeah? But I don't know. This, it's nice and all. Maybe it saves a bit of work, but it seems like a negligible advantage when facing the ocean of problems that is everything in NP, right? We still have this problem of, well, how do I know when I've caught them all, you know? How do I know when I've successfully given a polynomial time algorithm for every problem in NP? And for that, I mean, maybe it's a pipe dream, but wouldn't it be nice if there was one problem in NP to rule them all? One problem that somehow every other problem in NP reduced to. Then, if I wanted to prove that P was equal to NP, I could forget about everything except that one problem. I would only need to give a polynomial time algorithm for this one problem that is in this sense complete for NP. But I mean, surely, I mean, something like that can't exist. Look how crazy the reduction that we just saw was, you know? Could it really be possible that some magical transmutation of the hardness of problems in NP exists for every problem in NP all the way down to 1? It turns out the answer is perhaps mind-blowingly yes. There is a single problem in NP that every other problem in NP polytime reduces to, polytime mapping reduces to. We're going to say that a decision problem C is NP complete if it's in NP, and exactly what I just said, the pipe dream. For every problem A in NP, a polytime mapping reduces to C. So in particular, if I give a polytime algorithm that decides C, I have shown that P equals NP. And it turns out that SAT is an NP complete problem. That's this version of the satisfiability problem where the formulas are unstructured, right? They don't have to be a 3CNF, it's any Boolean formula. This is a result that, and this was the whole reason finding such a problem that would definitively allow us to prove that P was equal to NP. This was the motivation of the work of two researchers in the early 1970s, Stephen Cook and Leonid Levin. And they proved the result independently, with Levin's result or proof of the NP completeness of SAT coming out 2 years later. But that's only because he was actually trying to show that 21 problems were NP complete. And he was really trying to get a 22nd, but he delayed his release of this result quite a bit as a consequence, but finally just kind of threw in the towel. But yeah, and Stephen Cook is actually my fun trivia maybe, my academic grandpa. He was my advisor's advisor. Yeah, so I hope he's smiling down upon me now. He's still alive. I probably shouldn't joke about that. But yeah, so yeah, hi Grandpa, if you see this recording. Yeah, so what on earth could the proof of this theorem possibly look like? I mean, how? How do you transform all the traveling salesman problem, the subset something, three coloring, all these problems? How do you reduce them to a single, type of problem of some Boolean formula encoding, right? Well, it turns out we actually already kind of saw how to do something similar, right? Because like the one thing that all the problems in NP have in common is the definition, right? That there is a polynomial time verifier. So somehow, proceeding from that fact alone, we need to come up with a reduction to SAT. And there was a sort of a similar proof that we did not too long ago, where all you were given was the fact that, the computation of some other model of computation, in that case, just a Turing machine on some input. And you needed, knowing nothing else about the specifics of the Turing machine or the language that it recognized or decided whatsoever, to construct an instance that encoded just the computation of the Turing machine alone, that one fact that you could proceed from. Does anyone know which problem I'm talking about? Thought not too long ago. Yeah, PCP. Exactly. The post-correspondence problem. And so the proof that the post-correspondence problem was undecidable and the reduction from ATM there is actually morally very similar to the proof that SAT is NP-complete, except instead of transforming computation histories of unrestricted or unbounded Turing machines into PCP instances, sets of dominoes, now we want to transform polynomial time computations of verifiers and encode them somehow as Boolean formulas. And this is really the core idea, the heart of the Cook-Levin theorem. We don't really have enough time to see the entire proof, but the kind of core idea is that you can encode the computation of a verifier on input X and certificate Y as a polynomial size, because this is a polynomial time computation, formula phi that depends on the definition of this verifier and its transition function and the input X, such that there is a certificate Y such that V on input X accepts if and only if there is an assignment S to this formula such that it outputs 1. And now that you have this basic idea and armed with your knowledge of how to do computation history reductions, I am telling you guys, you could prove this theorem. Like, you have all the tools necessary to actually prove this result. It's just like, really all the difficulty comes in sort of handling all the cases, the way that we did in the proof of the PCP theorem, right? But you absolutely could, if you were adequately motivated, perhaps by an unreleased bonus problem of some sort, to prove this theorem. Yeah, the timing worked out pretty nicely. Yeah, that's all for today. Thanks for listening.